are the basic units of which elements are comprised of, although not the smallest. Today, knowledge of the atoms that make up our world is common, but this was not always the case. Lasse and I will be briefly explaining the development and history behind what we now know as atomic theory and atomic structure. Around 400 BC, a philosopher named Democritus from ancient Greece proposed that everything is made up of what we now refer to as atoms.
However, with little to no prior conceptualization in this field, he did not have a complete understanding of the atom. Democritus believed that the atom was indivisible, the smallest unit of matter.
Fast forward to the times of Aristotle, another ancient Greek philosopher, and we get his contribution to the atomic theory.
Aristotle thought that all matter was comprised of four primary elements: earth, air, water, and fire. If we jump to the late 18th and early 19th century, we find chemist John Dalton. He too thought these atoms were indivisible and indestructible, and that all atoms were identical in their physical and chemical properties.
Dalton also looked into the combination, rearrangement, and separation of atoms, or chemical reactions. He believed that atoms only form in single, whole number ratios to form compounds. In 1897, physicist J.J. Thomson suggested that there existed a smaller component to the atom that had a negative charge. He discovered what we now call the electron, known to be about 1,000 times smaller than the atom, through his cathode ray tube experiment.
With this, he developed the plum pudding model, in which the atom consisted of a large, positively charged spherical cloud with negative charges distributed within it.
The discovery of the electron paved the way for more accurate models of the atom. In the early 20th century, physicist Ernest Rutherford discovered the nucleus through his famed gold foil experiment.
He suggested that at the center of the atom lies a dense, positively charged mass he called the nucleus. Thomson's electrons then orbit the nucleus and was mostly empty space. This model is known as the nuclear model, or sometimes the planetary, solar system, or Jimmy Neutron model.
Just a few years later, in 1913, physicist Niels Bohr expanded on the nuclear model through his research into the light emission spectrum of hydrogen. Bohr put the orbiting electrons into energy levels, or the rings, that surround the nucleus.
With this, Bohr created his Bohr model, which is very similar to the Rutherford nuclear model, with the added level of specificity and energy levels.
With all the advancements in atomic theory and the development of the atomic model, there was still one unanswered question. How can an atom that is twice the charge of another have a mass that is 4 times larger? Physicist James Chadwick answered this question in 1932 with his proposal of the neutron, a particle with a neutral charge and approximately the same mass as a proton.
Again, Chadwick kept to a similar model to his predecessor, but added his newfound particle, the neutron.
As of now, the current standard for the atomic model is the quantum mechanical model, with quantum meaning the smallest piece and mechanical meaning how stuff works.
The quantum mechanical model consists of the nucleus at the center, surrounded by orbitals, or regions of space in which electrons are likely to be found. This model combines everything that is currently known of the atom, and for this reason is very difficult to draw.
Our knowledge of the atom, subatomic particles, its structure, and its behavior is ever expanded. Throughout history, many significant advancements have been made, and research is ongoing. Atomic mass is a property of an element that describes the number of protons plus the average number of neutrons scaled for abundance.
For most elements, there are several naturally occurring isotopes, meaning the element can exist with different numbers of neutrons. We use an average for an atomic mass number because in a large sample of trillions of atoms of a single element, there is no way that all the atoms would have the same number of neutrons.
To calculate the atomic mass of an element, you need to know the abundance of all the isotopes of the atom. The number of protons plus the number of neutrons of each isotope is multiplied by its relative abundance, then added together. The sum will be the atomic mass in AMUs, or atomic mass units.
For example, if you want to find the atomic mass number of chlorine without looking at a periodic table, you would find out how many isotopes there are and their relative abundances. In the case of chlorine, there are 2 naturally occurring isotopes that encompass 99.9999% of all chlorine atoms. These isotopes are chlorine-35 and chlorine-37. Next, you multiply each isotope by its relative abundance. So 35 times 0.7578 plus 37 times 0.2422, which equals 35.48914 AMUs.
Thank you guys for watching. I hope this was helpful in reviewing atomic theory and calculating atomic mass, and good luck to everyone on the final.